In the main video, when I said generalizing curl in higher dimensions, some of your immediate thoughts would be in differential geometry, we can replace it with the exterior derivative, which generalizes div grad curl in 3 dimensions. The argument of there being a vector potential is then generalized to the Poincare lemma. But what should this omega be? Before answering that, even for motion in more than one dimension, we can still define this vector field U. Let's define omega as a 2 form, which means it takes in 2 vectors and output a number. This number is the volume of the parallelepiped created by vectors u, v, and w. You have actually seen this before. The normal vector times area is precisely a cross product, and the scalar triple product is a volume. One thing to note is that this is a signed volume. If you swap any 2 of these, you gain a minus sign. One other thing to note is that when u, v, and w are higher dimensional, the volume of the parallelepiped formed by 3 vectors can be computed by something called the Gramian. More details in the description. Now we assume that d omega equals 0. In the 3D case, this assumption is equivalent to u being divergence-free. This is because in the 3D case, divergence-free means the integral of divergence over any volume M is 0. By divergence theorem, this is the flux across the boundary, but the integral of u dot n is the integral of this form omega, which, by generalized Stokes theorem, equals integral of d omega over m. Since this is true for all m, we have d omega equals 0. This assumption generalizes the divergence-free assumption to higher dimensions. What follows is very similar to the 3D case. Again, we have a potential theta that comes from our d omega equals 0 assumption. Because this omega is a 2 form, the potential theta is a 1 form. Now define the action as the integral of this 1 form theta. The difference in action is again the integral of theta around a loop, and by generalized Stokes theorem, this is the integral of d theta over any surface M bounded by the loop. But d theta is negative omega, so the difference in action is the integral of omega. For an infinitesimal variation from a physical trajectory gamma, the integrand is omega acting on 2 vectors. One is the tangent vector along gamma, which is given by u itself. The other is the direction of your variation. However, by definition, this is the volume of the parallelepiped formed by u, and w, which is 0 because there are 2 repeated entries. One thing that's left is the standard choice of this 1 form theta. Similar to the 3D case, this 1 form potential is not unique. We can arbitrarily add some differentials to it. However, we have a standard choice of theta, pi dqi minus h dt, guaranteed by the equivalent of Darboux theorem for contact forms. That's how to formalize the argument in higher dimensions. See you next time.